thing about the surface area is that actually justifying like I did for the arc length, it gets harder. So let me say this. Justification. The lecture review problem 1, 2, 3 that I do today is what I mean by justification. Why is it a good definition? That one is postponed to Calc 3. Right, this is Calc 3, where you learn 3D and together with a little bit of a linear algebraic idea. So you have to imagine this parallelogram that's hovering in the three-dimensional space. Can you imagine that? You know, um, I've seen that in some Superman movie that they're trapped in this glass and they're flying over in the universe. That parallelogram hovering in the universe. You actually look at the surfaces and dissect it into, although it's curved nicely, you have to kind of turn it into that kind of mirror. You've seen it if you go to some of the museum, nice surfaces in a mirror eyes, in the tiny mirror is actually flat, but overall it's kind of curved around. So you calculate the area of the parallelogram like that and sum it all up. That's the idea you can learn in Calc 3. Similar idea you can learn in here, but there will be no justification. It takes too much time in here to justify that's a correct one. So I'm just introducing the idea of approximation, but rest of the calculation we do our best, especially not ignoring the sum of many error terms, right? You can't. So the sum of many error terms is 0, right? Remember that part? Yeah. So we skip the justification, but we try to be careful with this one. You know, we have lots of errors added up, but also, I mean, there's small errors, but there are a lot of them. Then this is indeterminate form. Although errors are small, if it's so many, you can't conclude it from this many qualitative information. You can't conclude anything, right? So you just have to be careful and think about what happened, the triangle basis, right? That happens exactly because you ignore the errors actually sum up to a significant number, right? So we do that one, but we kind of skip that one. It's really hard for me to actually justify this is a good one. So here's the idea. We're not looking at the surface area of the general solid is a solid revolution. We look at something in XY coordinate system and you revolve it around, you have a solid, right? And then we think about the surface area of that. So we're pretty much looking at the object that are considered in disk method and washer method. All right? So here is y-axis, and here's x-axis, and I don't want to make it too complicated, so let me just introduce some curvy thing like that, just like this much. So this is a graph of y equals f of x. And when we're looking at the volume, I introduce the region underneath this curve. And then I talked about this region is attached to the axis of rotation, all that, right? And rotate it and get the solid. This time, we don't think about the region underneath the curve. Just this curve right there itself. All right? Keeping that relative distance to axis of rotation, and think about you rotating at this one. Then inside in here is hollow. There's nothing. There's not region is rotating. Just this one is a mark. All right? If it's rotated, you see that is kind of like this is a solid revolution. And inside is empty, right? It's not solid. It's just that surface, a thin surface. Make sense? And we're about to calculate the area of this one, of the surface area. All right? Idea of approximation is just like the line approximating the arc length of a curve. We do the similar thing. We actually divide it into, let's say, just several pieces in here. 1, 2, 3, 4. Only 4 pieces. Then you go up there and look at these points, right? And if you connect this one with a straight line, like that, like that. And the sum of all that thing will be arc length, good approximation of arc length to that one, right? But they actually wanted to replace that curve with this adjoint line segment and rotate that guy, right? Then would you agree that there's this point, that point, and that point? Instead of curvy part, we actually have this straight segment here, straight segment and straight segment that is rotated around like this. So the side is not really curved, but the straight line is, if you touch that with your hand, you can kind of see that it's kind of cylindrical, upright part, but it's not really upright. It's part of a cone. So idea is this one. You chop up into many, many pieces, and you look at the many, many line segment, and you rotate around, right? I think I've seen some architectural objects like that, and somewhere in Orlando, Disney World, somewhere there, they made it actually in that way, not like perfect surfaces. You have to fragment it into pieces like that. Okay. So the next part is looking at this piece. So there are 4 pieces. I'm going to take out one piece. I'm going to exaggerate like this. Is this thickness? And that's one side. And another side is like this. And here is that part. Does it look like one of the 4 pieces, the strip off there? And the key thing is that this side line is not parallel to x-axis, right? Kind of a little bit slanted. Okay. And here's the axis of rotation there. X-axis. So do you agree that is kind of part of the cone? If it is gotten from that piece right there, okay, from that piece right there, what you see in that over that part, if you replace it with a straight line, if you rotate that straight line, let's say if I extended that straight line like this, and you can see it eventually hits the x-axis, right? If I rotate the entire long segment, do you agree you get a surface area of a cone, right? So that's the only part of the cone, right? So it extends to a cone. Okay? So we're about to calculate the area of this side part, or actually strip part of the side area of a cone. And then you sum all up. So I'm going to call that surface area delta AK. Is that all right? So the entire surface area is nicely approximated by k going from 1 through n of delta AK. And our job is calculating this delta AK as accurately as possible. All right? The book approaches in the following way. You cut it in here and unfold it and claim that it becomes perfectly flat. There's no wobbly part. But you can, to me, it's not absolutely clear that you cut out a cone and unfold it and become absolutely flat. That part's a little unclear to me. So, well, lots of things are intuitive here, and especially beginning from here, but we have to do our best to avoid any ambiguous part and all. So I approach this parallelogram method. Kind of that's a better way to approach this one. All right. So let's calculate delta AK. Let's compute delta AK as accurately as possible. All right? So here, what kind of information we're using, it's something, thought out previously. So but there are lots of, so I'm going to exaggerate a little bit like here. It's really thick. Right? Does it look like a part of a cone there? It turns out knowing this information is useful, so I'm going to call that one delta L. So overall, it's kind of little pieces. The length of that side part is delta L. Right? Remember, in the arc length formulation, where is the formula? This is the formula for the arc length, right? And remember the meaning of this part in there? All together up to delta xk. So let me go back and write it down. 1 plus, before we enter definite integral, this is kind of formulation of the Riemann sum. Squared delta x out there. Remember that? So what was this quantities representing? Arc length, not arc. So in that, before we enter the arc length, we divided up. We looked at the triangle, right? And this is the length of which part of the triangle? Hypotenuse of each of the right triangle, right? So length of the hypotenuse here is kind of shows up in that form, don't you think? So that'll be part of our surface area formula. All right? So it turns out if we have that information, we can write that down neatly. With further exaggeration, I'm going to do the following. I'm going to divide this. You see this is a perfect circle, right? We're just looking at a different perspectives. It looks like an ellipse to us, but three-dimensionally, if you go over, it's a perfect circle. Suppose you evenly divided the circle into these pieces like this, and you extend it like this, and it creates this another evenly divided points around the circle. They're exactly five pieces, things like it, 500 pieces. Then we connect this one with a straight line. Straight line, straight line, straight line, and straight line. So although this is slightly curved, we replace it with a straight line. Okay? That straight line is going to be called delta S1. Delta S1 up there, and down there, delta S2. It's not that the second one is called delta S2, not like that. Every here, the length, all of the length here is a delta S, right? Because it's evenly divided. It's straight line the path. And the side length here, what do you think the side length of this part is going to be? Delta L, exactly. That's exactly the same edge around everywhere, right? So that's exactly delta L. Now with this 4 straight edges, this becomes a quadrilateral. This quadrilateral had a name. What is the name of this guy in here? Top is delta S1, down there delta S2, right? Side line is delta L, delta L. What is the name of this one? Where top and bottom is parallel to each other. Trapezoid, right? This is a trapezoid. If you flip to the front matter of the book, they tell you how to calculate the area of the trapezoid. All right, it's there. But the point is that this part is slightly curved, right? Slightly curved, but this one is perfectly flat. And the key thing is that if you do that with the smaller length of this one and smaller, that approximates the area of this part of the cone. That's another jump in that logic. All right? So that said, let's write that down. I call that one delta tk, so why don't I call the trapezoid region delta tk? All right? The area of this one is called delta tk. If you do that really many pieces around the circle, and that converges to the area of the side part of the cone. So basically what we're doing is that the cone is a fundamental case of the solid revolution. So we're relying on that estimation. Just like length of a straight line is a fundamental case for the length of an arc, then we use that to approximate others, right? That make sense? All right. Anybody remember area of a trapezoid? I don't expect that. You don't see that too often. Yeah, go ahead. 1/2, yeah. He's got the book. Or he remembered everything. 1/2 height. So height is not quite denoted here, right? So I'm going to call h. Height really means this guy in here. Make sense? H. That's h. Parenthesis. Top length plus the bottom length. That's the trapezoid. The key thing is that this delta S1 doesn't change. As we add up this one many times, h is always the same. Delta S1 is always the same. Delta S2 is always the same. Correct? Right. So let's think about this is the independent. This is the main parameter. Then delta S2, as we extend it, completely determined. And L is given because of all that shape. H is completely determined. All right? So let's write down H in terms of things that are important here. Delta L and things like that. So who wants to go for H? Pythagorean theorem, right? Pythagorean theorem. So Pythagorean theorem is h squared in bottom, and it's going to be L squared, right? So that's going to be like this, since we have the hypotenuse of this right triangle is delta L squared, correct? And you have to subtract off this guy, right? You can see exactly the same copy in here and there. So if you subtract off delta S1, you're left with the other two wings, and then half of it will be the correct one. So 1/2 of delta S2 minus delta S1, is that correct? Yeah, if you square that, that's going to be h. Horrible expression, but that's what h is in the exact form. Yes. Right, here is a delta S1, copy is coming down, and this one plus that one would be delta S2 minus delta S1. But because it's symmetric, half of it will be this one here. So delta S2 minus delta S1 divided by 2 will be this, both of them here. Make sense? All right. So that's squared inside the Pythagorean theorem. Everything is squared, right? So that's the estimate. Make sense? So how do you calculate the area around it? Consider the sum, k going from 1 through n, right? Delta tk. That will be the sum of these several trapezoid, flattened out version, correct? But if there are many, many of them, we believe this is really approaching that. So let's calculate that part. So here's 1/2 h and delta S1, delta S2, right? As k varies, if you look at this side and right next to side, is any of them here changing? Always constant, right? As you look around it here, all of these quantities are constant. H never changes, delta S1 never changes, right? So exactly how many copies are there of exactly the same thing? N copies, right? So it's 1/2 times H times delta S1, delta S2, N copies, correct? Right? So I'm going to distribute N there. It's 1/2 H out there, delta S1 times N plus delta S2 times N. And we want to put many, many segments of a trapezoid around it, right? So as N approaches what number? Infinity, correct? There are lots and lots of them. So I want you to go, somebody tell me, what could be the good approximation of delta S1 times N as N is getting bigger and bigger, and many, many, many segments are put around there. This is a copy of delta S1, right? And there's right next to it. Suppose there are gazillion around them here. If you add them all up, n times, what happens? So limit behavior. If you add all that little segment around it, all that is so tiny, it becomes circumference of a top circle, right? Is that right? Circumference of a top circle. So if I call that radius R1 of the top circle, then it's going to be 2 pi R1, is that right? What about the bottom one? If S2 is so small and you're going around all that, and then you have 2 pi R2, is that right? Correct? Yeah. What about H? What happens to H? You go back to the H formula. Delta L, does delta L changes as we put the more and more n's there? Delta is always there, right? We're only dividing just this part in here, right? Delta is always there. It never changes, correct? How about delta S2 and delta S1? What happened to those? Almost becoming 0, right? Individual delta, there's no n multiplied in here. Individual delta S2 is a very, very small. So would you agree that one approaches actually square root of delta L squared minus 0? Therefore, it's just a delta L. Okay? You can imagine if H is very, very small, this delta L is almost vertical. Think about it as a thin triangle. This side is almost vertical, becoming almost H. But this is better explanation. Okay? So this H becomes a delta L. Okay? So 2 pi is common. You factor it out. So 2 cancel and pi is out there. and R1 plus R2 and times delta L. That is the area of a side of a cone. Make sense? All right. Delta L didn't approach 0, but when you go back to our original setting, that this is delta L here, as we chop it more and more, this delta L will also approach 0, right? But we kind of estimated, calculate the side area in that way. So you don't have to unfold it. It's a better method of approximation, easier to understand. Any questions so far? So we go back to delta AK. So so that was only the delta TK summed up. So do you think we answered the delta AK here? That's the area of the side part, right? So that's what we have answered. We'll go back and summary, right? So thus, we answered delta AK has this neat formula of a pi times top cone, the circumference and bottom circumference. It doesn't matter because it's plus whatever the side is, it's just the sum times the delta L, which is the side length of that. Good? So if you just put, Riemann sum and that's it. If you can pull out the Riemann sum out of this, and that's the surface area. So you got a lot of choices and got it complicated. So I'm going to give you some result. I'm going to call that lemma. It's a bit sloppy just to explain to you and what happens to the little errors that are summed up is basically boils down to that. It's k going from 1 through n. And this g is representing just elementary functions, not too abstract or complicated. Sine and cosine, those elementary functions. That involves xk. You know what xk is, right? And you know what xk star is? Whatever the choice in between that, you made out of that. And maybe you have something else, xk tilde. Doesn't matter how many you throw in as long as it's finite. Maybe you have xk hat. This is like a wave symbol tilde and hat. These are all points in between xk minus 1 and xk, right? Suppose you fail to write this one in terms of xk star, one variable. Then you enter Riemann sum directly, right? But suppose you failed it. You have lots of them here. Lots of choices to get the better approximation. But strangely enough, out there, you don't have just delta, but you have a delta x squared. Suppose this was the case, and you can show as you put more and more points, this actually approaches 0. This is negligible. The key thing is that this delta x squared shows up. This is a key part. If it is a delta x, and then you have this one, then this error becomes something. But delta x is squared, and you can use one copy outside and make this one converge to something that one more copy of delta x actually kills everything. All right? So you will see that this type of thing shows up to when you approximate things correctly. So that's a lemma that'll make our calculation a little bit more understandable. All right? This is the part that is taking care of, sum of many small errors. Where is that sum of many small errors? It disappeared. Here, sum of many small errors shouldn't be just neglected. You have to be careful on that part, right? And this is the general lemma that takes care of it. All right, so the area of a side of that must be approximated nicely with the sum of all the side area, right? Side area here is denoted by delta AK. It's delta AK. And we just did some additional calculation. So the delta AK looks like, who remembers delta AK? It's actually written up there as a pi R1, R2, delta L. All depend on kth interval. right? So that's a formulation. So here is how it boils down. X there and Y. I'm not going to look at the whole thing. I'm just going to look at what happened and the kth interval, right? So we zoomed in, big kth interval, and here's a point. There's a point. It's actually curved side, but I replaced it with a straight line, right? That straight line. Okay. So let's think about delta L. I think I forgot to put LK in there, did I? Well, this is kth interval. This length is always different slightly. So I better go ahead and put this delta LK. Sorry about that. Delta LK. Delta LK here. That's it. Delta LK there. Each kth interval is different as well. So who wants to go for delta LK? In terms of the usual variable involved in the kth Riemann sum. Isn't that supposed to be square root of something? Right? Right? So that was delta x squared, right? Delta yk squared, remember that? And then we use something called mean value theorem. Remember mean value theorem? Use mean value theorem to rewrite this one. 1 plus f prime squared times delta x. I think I've stated that before. So who remembers what goes in here? In that space. It's not xk or xk minus 1, right? It's not x. Inside the definite integral is x, but it's a Riemann sum level, right? Yeah, it's a Riemann sum level. It's not dx, it's the delta x. Mean value theorem doesn't tell you what it is, right? It's just in there. So we use xk accent. For example, tilde. It's in between xk minus 1 and xk. We don't know. Mean value theorem only tells you there is one. Make these two things exactly equal to each other. Remember that part? Yeah. So there's some choice of value in between xk and xk minus 1 such that this is exactly equal. All right? That's the power of the mean value theorem. It's not approximating, replacing with approximation. That's exactly equal in a slightly different form. Make sense? So let's calculate R1. Who wants to go for R1? R1 was the radius of a kind of, let me give you the picture in here. Like this. Going back to side picture again. You see R1 here? R1 is this guy, right? Yeah. R1 is the radius of that guy. So what would be the good value in here? F of x k minus 1. Is that what you said? Yeah, that's exactly this length, and that's rotated, right? That's exactly R1. Yeah, correct. Yeah. R1 there. How about R2? Who wants to go for R2 there? Not Sabrina. Is that one, right? That's your R2. That's the radius. Yeah? F of xk. That's R2. So we got everything, right? R1 and R2 and delta LK all spelled out in terms of usual parameters involved in a Riemann sum. Correct? All right, let's write that down. So here is the area. Let's say area A, right? Capital A. That's better. Capital A is approximated by k going from 1 through n of pi times R1 is f of xk minus 1. R2 is f of xk times delta is 1 plus f prime of delta xk tilde squared and delta x outside the square root. Like that. Okay? So if you can turn that into a definite integral, and we have a good definition, all right? Assuming that's a good approximation. All right, here's another complicated trig, and how do we actually replace this one with a nice delta x, k tilde or something? So that's this is the idea. Use mean value theorem again. You remember how this mean value theorem involves f of xk and f of xk minus 1, right? So let's use that. Once again, mean value theorem says f of xk plus f of xk minus 1 divided by xk minus xk minus 1, right? Does it look like mean value theorem? It's a minus, actually. Right? This is supposed to be the slope of a secant line. That's exactly a slope of a tangent line, not at xk or xk minus 1, but elsewhere, right? Unless you use the accent different, like hat symbol. It's somewhere different from tilde, somewhere that two things exactly the same, right? So I'm about to replace its f of xk minus 1 with f of xk. So I'm going to solve that. I think it's easier to solve f of xk. So I'm going to solve that f of xk. Then I can replace f of xk with f of xk minus 1. That's correct. So you see that if you solve that, if you multiply that one is exactly delta x, right? Correct? So let's solve that one at a time. F of fk minus 1, xk minus 1 equals f prime of delta xk tilde times delta x. Is that right? I multiply both sides by delta x. And this one, next step, tells you that f of x, k, that is appearing in here, is f of xk minus 1, right? Plus f prime of xk tilde hat delta x, correct? If you solve this thing for f of xk, then f of xk has this form. That f of xk will be replaced by this one. All right? And it turns out from there you can write it as a Riemann sum nicely. All right, so here's the massive expression. A is delta k going from sigma k going from 1 through n. Here's a pi, and here's f of k minus 1 plus that whole thing, f of xk, is replaced by that. All right? All in exact calculation. That's the whole point of doing that. F of xk minus 1 plus f prime of xk hat and delta x, and outside there's that all the other stuff. I don't want to repeat it right now. Is that okay? That stuff is exactly that part right there. Okay? Delta x is out there, and this guy has one more delta x. So that part will have delta x squared, right? And that's why that part disappears. So let me write that down again. This is a sum. So I'm going to separate it, k going from 1 through n, pi times, I'm going to simplify these two things. I have enough motivation to simplify that part, right? What is that? 2 times f of xk minus 1, correct? And this part in here, oh, I have to multiply that stuff. And that one is distributed to that part and distributed to that part. And here's 1 plus f prime of xk tilde squared delta x goes there plus this one's multiplied there. So it's be careful. Okay, going from 1 through n and pi f prime xk hat, and there was outside the delta x. The two copies of delta x shows up. There's a delta x, and the stuff part also has delta x, and times is all that stuff. All right. So this one is made out of function elementary function values that involves xk tilde and xk hat, but it has delta x squared, right? Therefore, according to the lemma, because of the square part, this whole thing approaches 0 as that approaches 0. And what other things that we need to calculate in there is one more substitution. So I'm going to just do this briefly by another mean value theorem. Maybe I should have done that, but it's a 3 values, so you have to do it separate like this if it is one mean value theorem. If you want to replace that f of x k tilde, this one with f of x k tilde is also f of x k minus 1 is a smaller, so we can rewrite it like this, f of x k tilde plus f prime of, this is the third value, so I'm going to do the double tilde and times the delta x. So if you use the mean value theorem one more time to xk minus 1 and xk tilde, and you get this one just like we did it before, so I didn't repeat it. So we get it like this, and this f of xk minus 1 is replaced by this one, and then you have delta x and delta x again. So here is this expression that you want to never see this again. So this is look like this. 2 times f of xk minus 1 is replaced by f of xk tilde there, and then other stuff is still out there. F prime of xk tilde delta x. There's no delta x in there, so we only have 1 copies of delta x. Second part is this one has a 2 terms, so these rest of the part is multiplied to there. As you can see there are 2 delta x's. There's that k from 1 through n. Here's a 2 pi multiplied to those guys, so that's replaced. So we have f prime xk double hat, and delta x is already out there, and this term has one more, is a k star, and then there's this square root inside. That's fair to look like this, and then here the term that approaching 0. But because of this delta xk delta x squared, this whole thing also approaches 0 as we put more and more. So this one here is exactly delta xk tilde and xk tilde and xk tilde all in one variable, right? We keep replacing this something that we don't want using the mean value theorem. When you sideline those unwanted terms, fortunately they all have delta x squared, right? Therefore, as we put in more and more n getting larger and larger, this term becomes 0 according to the lemma. Delta x squared is a too much vanishing factor, so it becomes 0. So that approaches eventually. This one is exactly everything in terms of the xk tilde, right? So then the Riemann sum, that changes to 2 pi f of x and xk tilde again, so it's exactly 1 plus f prime. I missed the squares everywhere and only at that part. So f prime of x squared and dx, and that is the formula. Okay? So let me go back before we take a short break. Let me go back in here, summarize it, what just happened. The answer here, let me do that in a different color. Answer I'm writing on here is that going a from a to b, 2 pi f of x, right? 2 pi f of x times 1 plus f prime of x squared. All of these factors are familiar, right? What is good interpretation of a 2 pi f of x? In here, in that functional situation. If I just take that and I have this f of x value, and 2 pi f of x is circumference of that, right? Circumference. How about this one? Square root of 1 plus f prime of x squared. What is a good interpretation of that? It is kind of arc length. What's a better little right? This side length right here, the length of that side part, is a good approximation of arc length. So they're saying the radius times the length of that one is the area. How simple? Of course, right? That's the reaction, but that's the careful deduction from the area of a surface area of a cone. All right, let's remember it this way. 2 pi f of x, that's the radius of a rotation, right? At place x. And we multiply by the side length, but not horizontal length, the slanted length, right? The slanted length is coming from the arc length. Root 1 plus f prime of x. So it's like arc length, local bit of arc length, and times the circumference that correctly measure the surface area. All right? So let's take a short break. So 120.